In the last video, we talked about the sampling distribution of the sample mean, which is X bar, and particularly what we could do with it if our population was normal. But what happens if it is not taken from a normally distributed population? Okay, we're going to look at this in class just so that you could really see. But what happens is that when you start out with a small sample size, then your sampling distribution tends to not be normal. But as you get to a larger and larger sample size, your sampling distribution looks more and more normal. This is called the central limit theorem. The central limit theorem says that when n, which is our sample size, is large, the sampling distribution of X bar is approximately normal, no matter what kind of shape your distribution has. Okay, the question is, how large is large? What quantifies large? For us, large is any sample size that is greater than or equal to 30. Now, in the real world, it's probably going to vary from field to fields, like social sciences to medical stuff. Maybe even from statistician to statistician. But for us in AP, large is anything greater than or equal to 30. Okay, so let's look at an example. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that students at our school are typical texters, how likely is it that a random sample of 50 students will have sent more than a total of 1,000 texts in the last 24 hours? Okay, notice you might say, well, we're working with X bar and this is totals. So what's a way that I could think about this? Well, if I ever see total, I can think of that as if I want a total of 1,000 and I have 50 students, on average, how many text messages would each student have to send? And that would be 20. So what I'm going to say here is let's let X bar be the average number of texts sent by a student. Because we're working with X bars anyway, and total is not going to give me X bars. But if I look at total in relationship to my sample size, then I can get an average. So X bar is going to be the average number of texts sent by a randomly selected high school student. Okay, so I'm dealing with the sampling distribution. And in order to deal with it in a normal way, which is the way I really want to deal with it, I need to look at the sample size. Because my sample size, n, is greater than or equal to 30, okay, which it is because n is equal to 50, I can assume the sampling distribution of X bar is approximately normal. Okay, well, if it's normal, I want the stuff I usually have. I need a picture, I need a mean, I need a standard deviation. The mean is easy. I know that the mean of X bar is equal to the normal mean, which is 15. And the standard deviation of X bar would be 35 divided by the square root of 50. And I also need to say that 50 times 10 is 500. And there are more than 500 high school students. So that takes care of my 10% condition. So now I have a mean and a standard deviation, and I know it's normal. So next thing up would be my pictures. So I'm wanting to say, since I'm looking for 50 students to send more than a total of 1,000, that means I'm looking for each student to send more than 20. Okay, well their mean, we said was 16, 15. We said the mean was 15. I'm looking for them to send more text messages than 20. Okay, so on average, how many text messages does someone send? I'm looking for an average of over 20. Okay, for the 10 people. So I take this, I do my z-score, 20 minus 15, divided by my new standard deviation, which was 35 over the square root of 50. I'm going to get a z-score value, which I'm then going to plug into the calculator, and I'm going to get a probability that I have an average of 20 or more texts is 0.1562. So there is about a 16% chance a group of 50 students will send more than 1,000 texts, because there's about a 16% chance that each of them will average over 20 texts. And there you go, the same process, except at the beginning we had to add that little statement that said, even though my population is not said to be normal, since my sample size is so large, I can assume my sampling distribution would be.